Okay, this week we have five problems again. First three are easier, and then the last two would take a little bit more time to explain. So let's get right to it. Um, First problem, magic tricks. If you read the problem, basically the idea is that you're given a string of up to 50 characters, only lowercase letters. And the question is if somebody were to swap two letters of their choice, two different two letters in different positions, would you be able to notice? If you can notice, you say one, otherwise you say zero. So the first string, no matter what two letters they swap, you would always be able to notice. And the second one, apparently you can't. Now, if you think a little bit about this, you'll realize that the only time when you cannot figure if somebody have swapped, if they've done a swap, but you don't know if they really did, is when there are two letters that are the same because they could have taken those letters and swapped them and you wouldn't know if any changes have occurred. So it's a roundabout way of asking, are all the characters in this string unique? And then there are many different ways you can do it. You can just, go through the string and count how many A to Z there are. There are only 26 choices. So if any of them have more than one, then you know that you have non-unique characters. You can sort it and see if there are any characters that are occur consecutively. That's another way. Um, the way I did it may not be the most natural way for most people, but I make use of STL. So I use a function called unique. So I take the string and ask if it's unique. Now, unique doesn't work the way that many people think it does if um, you don't know how it's supposed to work. The first thing is unique will only work if you sort it. So everything has to be sorted. And unique is an algorithm that works not just on strings but on any containers. So the first thing that you must do is sort it. Then when you call unique, it's going to return an iterator to something. Now, what exactly does unique do? So let's actually give you explain what unique does. So first of all, it must be sorted. If it's not sorted, you're in trouble. So maybe you have something like this. Okay, so here's your container, and it could be an array. And this is, of course, the start, and this is the end of the container. Unique, it's going to take a sorted container and make every element in the same order but unique. So it will remove the duplicates and it will return an iterator. And I'll just put question marks here. The rest of this container, you cannot rely on the content. And it will return, and this is the return iterator that points to the end of the unique section. In other words, the distance between start all the way to return, it's the number of unique characters there, unique elements there in this container. So if I want to make sure that everything is indeed unique, I want this to point to the end, meaning that I did not actually remove anything. And that's what I did here. So I called unique on the whole container, and if it returns the end of the container, then it means that everything is unique. Okay, otherwise it's not. Um, so again, this I don't know, maybe this is an overkill, but I want to show you how this unique function works in C++. It's not just about finding out whether all the elements are unique, but also it can remove duplicates, um, and then you can resize. So if you want to, for example, really remove a duplicate, let's say you have a vector. So if this is a vector, so v, oops, oh, what happened? Okay, so if this is a vector v, right? So v dot begin and v should just start begin. I can then say, so the unique begin v and v, that will return wherever it ends after all the duplicates are removed, minus begin v, so that would be the number of elements that are remaining, so all the number of unique things, and then v dot resize. And that will shrink the container to only contain the unique elements. Okay, again, this is an overkill, perhaps, but um, you can write also solve this problem in many ways. I prefer to use STL if I know the appropriate STL function, just because it's easier for me to remember um, and not screw up, I guess. Of course, you have to know your STL. All right. Next problem, army strength. All right, so um, you have two armies. One is called Mecha Godzilla, and the other one is called Space Godzilla. So basically, Army One and Army Two, and they fight in different rounds. Each round, so all the monster in the armies are represented by a number. Big number means strong. Small numbers means weak. And then each time they battle, the weakest of all the monsters that are still alive is killed. If there's several weakest monsters, but all of them are from the same army, you kill one of them at random. If both have at least one of the weakest monsters, a random weakest monster from the Mecha Godzilla army is killed. The war is over if one of the armies of all the monsters are dead. And the dead army lost, the other one won. Okay. So basically, if you were to just follow this, you repeatedly look for who is the smallest, right? Who is the smallest one that's still alive, and then kill one of them based on these rules. And then when one of the armies are dead, then you know which one wins. Um, so the only thing that you have to worry about is, if both armies' weakest ones still alive are the same, then you're supposed to tie break by killing the Mecha Godzilla. So I suppose you can just simulate, repeatedly choose the smallest one from each group. If they're not the same, then you kill the one that's smaller. If they're the same, you kill the one from Mecha Godzilla. There's a problem. The problem is that each of these armies is at most 100,000 big. So totally, there are 200,000. And if you keep sorting it over and over again, that would be too long. So this is a classical problem where you want to be able to continuously oops, why is it always flipping back to this? You want to continuously repeatedly do something. And what is it that you want to do? Find the smallest item in each army, okay? And possibly, so maybe, remove the smallest item, depending on whether your army smallest item has the one that's killed. And if you have done some data structures, what is the correct, or what is the data structure that allows you to easily find the smallest item and maybe remove it? And that's a priority queue. Or also, it's also called heap. But in C++, it's called priority queue. And every operation has log n time for, well, finding it, the smallest item is easy, it's constant time, but removing is log n time. So if you do it 100,000 times or 200,000 times, that's okay because that's n log n, right? N log n for 200,000, it's not bad. So you can just do that at the beginning stuff. Use two priority queues, one for each army. And at every step, just ask who is the smallest item from each army, compare. We move the smallest one, or if there's a tie, we move the one from Mecca, and you keep doing it until one of the queue is empty. And then the other queue would be the one that's a winner. Good, you can do that. But actually, you don't have to do that. You can actually do it much easier. If you imagine sorting stuff, sorting the two armies, so one of them is A's, we sort all the numbers, call it N and M, and the other one. And if you start doing this process, you start getting rid of the things at the low end, right? Maybe this one, and then maybe this one, and this one, and so on. And when are you actually going to kill an army? You kill an army when you either get rid of this one or you get rid of this one. That's the only way. So when would the first army lose? Right? They have to get rid of this one. And the only way you can get rid of this one, it's if this maximum, the biggest in the strongest in the first army, it's less than or equal to, so this is the Mecca one and the other is space. If the strongest one, it's less than or equal to the other one. Why is less than or equal to? Because tie break, if both are the same, you kill the Mecca one. And you, so if the strongest one in the Mecca one is not as strong or not stronger than the strongest in space, eventually this one will get killed. And similarly, if, or I guess conversely, if the strongest one in the Mecca army is bigger than the strongest one in the space army, and eventually this one is going to get killed. And this will never get killed. The strongest one will never get killed. So yes, you can simulate it, the every step of the way until it works, or it is actually much faster to just look at the maximum because you can do this. So if you use the priority queue way, it's n log n time, whereas finding the maximum and comparing is linear time. So this is better. Now, is the other one good enough? So we have to go back to the problem statement and say, well, what is n? N is approximately 200,000 because they're at most 200,000, 100,000 in each army. So you have to do at most 200,000 rounds. So I guess this n and these two are sort of different n's because this is the number of rounds, which is the total number of monsters. And this n is actually the size of a single army. But if we use 200,000, it's more or less okay because it's the upper bound for both n and log n, whether it's 100,000, 200,000 is about the same. And then, but then you don't do it just once, you do it at most 50 times. So 50 times n log n, and then you have to look and see how much time limit they give you. 1 second. I'm actually not sure if this is fast enough. Um, I guess we can give it a try. Actually, why don't we? Oops, not here. We can give it a try right now. I'll just do coding right in this little terminal. So we'll read in the number of cases, and then I do always like this. So I'll do everything in this solve function. Oh yeah, they asked you the three possible answers: Godzilla, Mecha Godzilla, or uncertain. The uncertain can actually never happen. So solve. What are the inputs? So inputs, it's NG and NM. The size of the two armies. And then we have two priority queue. Now the priority queue actually normally um, find the maximum number since that's the smallest number. So we're going to play a little trick. Well, there actually are different ways you can do this. So let's do it maybe int. This is a way, maybe it's the easiest. Like this, um, with the two armies. I'll call it uh, army G and army M. And can I hide? Yeah, let's get this bigger. And then now I forgot what the problem statement says, so I'll have to read it. And then two lines follows. First is NG Godzilla's and then the Mecha Godzilla. Okay. So then I read for int I equal to 0, I less than NG I plus plus, int X, C and X, and then army G dot push X. And then I do the same thing. So I probably could have, I don't know, written this in a function. So I just call it, but anyway, I read into two. So now, wow, army G, so not army G. So let me see here. Wow, not army G dot empty. So wow, they are both non-empty. That means I still have to do something. And then at the end, I say if army G is empty, actually, let me do it this way. If not army G is empty, so that means G army G1, what am I supposed to write? Godzilla. C out Godzilla. And then else C out Mecha Godzilla. Okay, so that's, so now I have to say G monster equals to army G dot top. So that would be the smallest one. Army G and monster equals to army M dot top. So if G monster it's less than M monster, so that's the only time that army G is removed. So army G dot top. Else they're either the same or M is smaller, so I remove army M dot top. And I think that's what I have to do if I haven't screwed up. It's always dangerous to code unrehearsed. So it works. Okay, so this is fast enough even there, but this is 0.17 seconds, it says, and 0.13. So it's not a huge difference because it's relatively small, but here I don't really do any of the priority queue. I just find what is the maximum element of each of these, and then just compare the maximum. Okay, anyway, you can do it either way. The more, I don't know if you call it straightforward way is to use a priority queue. And then the second way is to use just compare the maximum and to realize that the maximum, the bigger, the strongest monster in the army can never be removed. Okay, musical scales. Um, this is a little bit messy, I guess. The problem itself, I think it's sort of straightforward in terms of algorithms, but it's messy. So I want to show you how I do it to make it less messy. Okay, so you have these musical notes in increasing order, A sharp, B, whatever. And the difference between consecutive notes is semitone. So one step, they'll tell you that this means one step. And the sequence wraps around so that the note that is one semitone above G sharp, it's A. So this is kind of some kind of modular arithmetic. The difference between a tone is the same as two semitones. So tones are two steps, semitones are one step. And immediately, one of the things that I wanted to talk about is to make it easier, because we're going in circle, we want to just give these numbers 0, 1, 2. So we'll give these numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then we do everything mod 12. So if you do 11 plus 1, mod 12 will go back to the beginning. Okay, so the first thing that we want to do is find a way to convert these strings into numbers, 0 to 11. Okay, and then what else did they say? We do not worry about flats, blah, blah, blah. Okay, we do not worry, so we don't worry. A major scale is defined by a note, such as A, C sharp, or whatever, following in an arithmetic. So +2, +2, +1, and so on. So you have to kind of do some arithmetic to figure out which ones. Starting note appears in the name of these scales. For example, A sharp, you go from A +2, +2, +1, etc., etc. Note that A sharp major is typically not considered as a music standard. It's identical to E blah blah blah. Okay, we ignore such problems and just okay. Finally, in this problem, the sequence, a song is just a sequence of notes. Your job is to identify all major scales such that the song uses only notes in that scale. All right, so you have a bunch of, so this is a song, and you have to figure out all the notes, all the major scales. So basically, you can only have at most 12 different scales, right? Because there are only 12 starting points I gave you. And for each one, you can figure out all the legal notes by following this. And then it's just a matter of asking for each of those scale, is there anything illegal in your song? And if not, then you're good. If it's illegal, then it's not good. So basically, we want to be able to say, let's generate all the musical scales, 12 of all the musical scales, so 12 of them. For each one, generate all the legal tones, legal notes, and then just check. There are only 12 of them. So the question is, how do we organize all of this? So the first thing that we're going to do is find a way to convert all the nodes into 0 to 11. And the way that I do it is I simply write an array of strings in the order that you want, right? So the first one is 0 and so on. And whenever somebody give me a string, I'm just going to do a string. I'm just going to do a search in this array, and it will tell me the index. Okay, so that's the first thing. I'm going to do a linear search. Don't worry about linear because it's only 12. It doesn't matter if it's linear or slow. So just find a way to convert the strings to a number. Okay. Then I'm also going to store this offset, the tone, tone, semitone, and so on, just to remember that to get all the notes in a scale, it's +2, +2, +1. I'm just putting in the array because that makes things a lot easier when I do things, as you'll see. And then I have 12 different scales. Each scale is a vector of strings. So each scale I will have a vector of all the nodes that I'm allowed to use. Okay, so at the beginning, I'm going to generate all the nodes for every scale. So for each scale, so there are 12 of them, First, index is my starting point of my scale. It starts at each possible position. And I'm going to push back the note, right? If the index is 3, then it will be C. If the index is 4, it will C sharp and so on. So I push for that scale, the starting point. And then for each of the 7 other nodes, index plus equals the offset. So it's either +2 or +1. Then I mod 12 to make sure that I'm in the right range. So if I go over, I go back into this circle and I just push it back. Now that I got the index, I push back the node. So this loop here, this double loop here, will look at every single one of the 12 scales. And for each one, add the 8 nodes in this scale. Now I read in the song that you give me. And then for each of the 12 scale I just asked, first, I assume that that scale is good. And then for each of the notes in the song, I ask, just find me, is that scale? So find that, so this is linear search. I find in the scale that I'm testing the note that is in this song. And if it's found, then it's good. And if it's not found, then it's bad. So this comparing not equals to and, that means it's found. Because in linear search, it will return an iterator to where it's found, unless it's not found. And if it's not found, it will return the end of the container. So here, this is saying, is it not found? Sorry, is it found? So return true if it's found and it's false otherwise. And then here, I'm basically saying, pick whatever the value of good is, which is Boolean, and do a Boolean AND with this result. So if it's true, then it won't change anything. But if it's false, it will set it to false. So if I find any node that is not in the scale, then good is false. And if at the end, good is still true, that means that I haven't found any bad scale, bad nodes. So then I can print out that scale. Okay, so anyway, you can read this carefully. There's nothing algorithmically that's difficult. It's just basically a linear search in multiple ways. But I want to show you how I organize my code so that it's a lot easier to deal with. I probably could have broken things up into functions and so on to make it easier to understand. But the point is that by using arrays to seed the array from the problem statement, then you don't have to have all the special cases. Do I go 2? Do I go 1? Once you put it in the array, you can just loop through and just read the value of the array. And then you can code the same way. So that's a little trick. All right, the last two requires a little bit more explanation. Okay, so the fourth problem is about this called abstract painting. And the idea is that you have R rows by C columns. So this is 2 rows, 3 columns. Each square will have 4 edges, but some might be shared in the middle. And each edge, you can color it in one of 3 possible ways, red, green, and blue. But there are some constraints. So all edges must be painted with exactly 1 color. And for each unit square, exactly 2 colors must be used, and each color must be used for exactly 2 edges. Right? So here you have red and green, both taking 2 edges, and here you have red and blue and so on. But here, this one is bad because you have 1 square with 3 blue edges. That's not allowed. So now you're given R and C. You want to know how many different ways you can actually color this. R is at most 14, C is at most 2000. So this is pretty big. You can try them all. They're at most 5 cases. And the numbers are actually very big. So you're supposed to produce the answer mod this big number so that the answer is not gigantic. Okay, so this is combinatorics. Maybe the best thing to figure out is whenever you have a problem like this, start small. Oops. Right? Figure out, can we do it for the smallest possible answer question? So the smallest possible question is 1 square. How many ways can we do this? Well, you can do blue. If you take these two as blue, let's say just blue and red, then these two must be red. Or it could be this one is blue and this one is red. And then you might have this one is blue and this one is red. Or it could be like this. Okay. So if you decide that the top and the left are the same color, then there's only one way. But wait, actually, because we have 3 colors, there's also the other way. Okay, so there are 2 ways. If you decide that the top and the left are blue and red, then there are 2 ways left to continue. You must use red and blue, but then it can be opposite. It can be either one. So what do I want to say? Once top and left is fixed, there are 2 possibilities left. Okay, so this is the first observation. So, but why do I choose blue and blue or blue and red? Why do I choose red and red and red and green and all that stuff? Well, it doesn't matter because there's 3 choices for the top. There's 3 choices for the left. And once I chose these 2, there are 2 more possibilities, either any one of these configurations. So altogether, it's 3 times 3 times 2, which is 18. Okay, so if I have exactly 1 square, that's the answer. Okay, so now that we have done 1 single square, let's try to do something a little bit harder. Let's imagine that I have 2 squares, one on the side by side. Now, I will still do the same thing for the first square. Okay, I have 18 choices, so there are 18 choices for this. And now that I've chosen one of the 18 choices, this edge has been fixed. Now, I'm using the same argument. There's 3 choices here. And now the top and the left are fixed, so there are 2 more choices. And if I have one more, it's the same thing because now this one has been chosen. It's already fixed, so it's another 3, another 2. And actually, you can come back and say this is just 3 and 3 and then 2, like that. What if you add one more on the bottom? It's the same argument because now if you have already done this one, then this is fixed. So you have 3 more choices here. And then once you fix the top and the left, you have 2. And now what about this one? Okay, so this one is maybe you think, okay, now we have fixed top and left. There are 2 more choices and so on. So if you think about it a little bit more, you realize that all you have to do is actually just choose all the colors of left and top. And then for each of the squares, you have 2 ways to choose it. So the answer is actually the number of rows. So this is number of rows, number of columns. Each one has 3 choices. So there are 3 raised to the power of row plus columns. And then you have R times C squares. Each one has 2 choices. So that's the answer. You compute this and you're done. Now, of course, this is going to be really big for big R and big C. So that's why they asked you to mod it with this 10 to the 9 plus 7 modulus. So what you have to compute, it's basically this mod m, where m is this 10 to the 9 plus 7. All right. How do you compute this? So first, we want to compute this mod m separately. We want to compute this mod m separately. And then once you know the answer, then you can take these two and then multiply mod m. Now this is pretty big. This is a billion plus 7. So this is just at the boundary of a 32-bit integers. So if you take these answers, right, each one is going to be less than m. So each one is going to fit in a 32-bit integer. But when you multiply these two together, it can go to 64-bit before you mod m. So you must make sure that you use 64-bit integers a long. So you take these two answers, multiply them, and then mod m, and then you're good. And then what it remains is, how do you compute exponentiation mod m? The first thing is, I guess the easy way out is to say, this is in my code library. It's called expmod, E-X-P-M-O-D. So you can go and look it up. Or you can use maybe you have seen this algorithm before. It's called fast exponentiation. So I'm not going to really write the code, but I'll just kind of explain how that works. So if you want to do, I don't know, 3 to 1,000,001, or whatever it is, 100,001 mod m. Okay. Whenever you see something that's odd, you get rid of the odd parts and you just write this. Okay. So you recursively compute this mod m. Then, so you recursively compute, um, let me write it better. You recursively compute this, and then whatever the answer comes back, you multiply by 3, and then mod m. Okay, so that doesn't seem like much of magic. But now, whenever you have an odd number, when you do this will always be even. And this is where the magic starts. You write this exponent as half of it, and then multiply by 2. So what you're going to do is you're going to recursively compute the answer for half the exponent and then square the result, mod m. And then because this is odd again, so this is even again, you can do the same trick and you can recursively compute this. I'm not going to write the mod m anymore, square. And you can basically every time reduce the exponent by half. And it wouldn't take too long. Right? This is basically log n steps. Of course, every once in a while, the exponent could be odd. And then you have to do this trick to get rid of one copy. And then you can do this reduction of by half again. So that's the idea. And this is called fast exponentiation. And if you go to my code library, you can find that, or you can just, I don't know, write it yourself. But this is basically a short way of doing this without using recursion. This is an iterative way, but it essentially says this is a bit operation and asking if the least significant bit is 1, meaning it's odd or even. If it's odd, then you subtract 1. Otherwise, you divide by 2. That is right bit shift by 1 bit. So that's the same as divide by 2. And if it's even, you square things. Otherwise, you multiply something in. Anyway, either you write your own or you copy mine. Doesn't really matter. But the point is that the answer is just 3 raised to the power of r plus c mod m, mod this thing. So here's the mod, times 2 to the r times c. Okay, and then here, because things blows up, you have to make sure that at every single step you take mod m, so things don't get too big on you. Anyway, that's this problem. So it's a little bit of combinatorics, a little bit of counting to figure out what you have to count, and then the most important thing I would say for this type of problem is try to figure out the smallest possible case and work your way up, because a lot of times that will help you. So smallest possible case. It's usually you can do it by brute force counting, and then hopefully, as you work your way up, you can see a pattern. Okay, last problem: exploding battery. Okay, so you can read the problem, but maybe I'll just explain it here. So you have a battery, and this battery can take a certain number of current. Why does it keep flipping this? The current it can take could be anywhere from 1 all the way up to some number 4711, is it? Let me just quickly check. 4711. Okay, and with this battery, oops, with this battery, it's going to take a certain amount of current, but at some point, at some unknown point, it's going to explode. It's going to be too much. And there's this property that if the battery, if you put in a current less than this point, it's never going to explode. So this is safe. And if you try to put any amount of currents from this unknown point and up, it's always going to explode. And your job is to figure out, well, okay, the problem is that you want to try to figure out exactly what this point is. Now, you're also given an n, the input, which is a place that is for sure going to explode. So the input is a number that you know for sure the battery will explode. You don't know where exactly this unknown point is, and you want to find an efficient way to measure to figure out exactly where this point is, the smallest point at which the battery will explode. The other thing is you're given 2 batteries. Now, why is it important that you have 2 batteries? Imagine that you have 1 battery. Suppose you only have 1 battery. What are you going to do? Well, if you don't know where this point is, right? You don't know where this question mark is. So you're going to put some current in and see if it explodes. So maybe you put it here. Or maybe let's say you put it here, it's safe. If you know it's safe, it hasn't exploded, whatever you put, then you know that the answer is above you, so you can try something bigger. But maybe you're not so lucky. You try something, whatever you try, and the battery exploded. Maybe you try it on this, you try some number and you just put it in and the battery exploded. The only thing you know at this point is that the answer is to the left. Well, it could be this point. It could be this point or to the left. You don't know what the answer is, but worst of all, you have no more batteries because it exploded. And so you have no way of checking. So if you only have 1 battery, the only possible thing that you can do to be able to figure out precisely when it explodes is to try every single one from 1, 2, 3 all the way up. It will just, you cannot afford to skip even one, because if you skip one and it exploded, you don't know if the answer is where you just test it or to the left of it. So the only way you can do this is by testing one at a time until it explodes from one and up. Okay, that is the only way. All right, so what does two batteries help? What does two batteries, why would two batteries help you? Well, with two batteries, you're allowed to take some risks, right? So you can take a stab here, and if you're lucky, it hasn't exploded, so you can still use two batteries. If you're not lucky, then it exploded, and then you can only use one battery, but then you can use the one battery to scan up, not have to go all the way up. So here's basically what you have to do. So you are given an input N, you know for sure this explode. And now the question is, where do you have two batteries, where do you test the first one, right? Where do we test the first one? I don't know, but let's call it T. So we're going to try T, and T can be anywhere from 1 to N minus 1. Why do I not check N? Because I know that for sure N explodes. This is the input. They tell me that N explodes. So the question is, so maybe I haven't actually told you what the question is. The question is, what is the fewest number of tests I need to do to guarantee that I'm okay, that I can find the exact spot where it explodes. Okay. Now, if I know for sure it explodes at N, the real value could be anywhere from 1 to N. I don't know where it is. And I want to use the fewest possible test to make sure that it doesn't matter what N, it doesn't matter what the number is, what the real number is, I will always be able to find it in that number of tests. So of course, if I just test every single one from 1, 2, 3 all the way up, I will always find it. But in the worst case, it's N minus 1. So if I only have one battery, the worst case is N minus 1 because I have to test every single one of them. Now, two batteries, I can take a step somewhere. But where's the step? I don't know. But let's imagine that I know. So let's fix the first thing. It's T. So my first test is T, wherever that may be. Now, there are two different possibilities. Maybe T is safe and maybe T is unsafe because I don't know where the answer is. It could be either side. So let's see what happens. If T is safe, okay, that means I still have two batteries left. So I know this is safe for sure. I also know that all of these are safe. So what that means is that I now know that the answer is somewhere here. How many different things are here? It's N minus T. Right? I got rid of T values before I have N minus 1 value. Well, if I count the N as well. So if I have a function, f of N, it's the minimum number of tests to answer for input N, where I know that N, it's guaranteed to explode, but I don't know anything else before that. Then I am reducing. So with one test, I'm reducing the problem to a smaller problem that looks the same, right? I still have a range where I don't know anything about the numbers before that, and I know that the last one is going to be exploding. except that my range is smaller. So recursively, I can say f of n minus t, I still have 2 batteries left, so I'm with 2 batteries. That's important. And then plus 1, because I used one test already to get to that point. So there's always a plus 1. If, on the other hand, this is unsafe, so that's the other option. If it's unsafe, then I know that all of these things are unsafe as well. And my answers are over here. But I now, because this is unsafe, I now lost a battery. So I have lost the battery. And the only thing I can do now is to check everything one at a time from 1 up to t minus 1. Okay. So those are my 2 options. I don't know the answer. It could be either way. If I want to minimize it. So if I, sorry, okay, let me do this again. Because I don't know whether the correct answer is to the left or to the right. When I take a stab t, it could explode or not explode. And I have to take the worst case. So I have to take the maximum of these 2. So if I decide to fix a particular t as my first test, then the number of tests I need to guarantee that I will find the answer no matter where the answer is the maximum of these 2 things. Maximum of f of n minus t plus 1 and t minus 1 plus 1, which is just t. But I don't know what t is. I want to try all the different t's. That's my first step. So if I try all the different t's, I want to minimize this number. So I want to try all the different t, and whichever t gives me the minimum of this value, I want to take that t. And that's my answer. Okay. So I use 0. I think I used 1 base instead of 0 base or something like that. So as I started 1 instead of starting 0, so things are a little bit slightly different, but basically, oh no, it's the same because I took the 1 outside. So I try all possible t's. I use I, and then it's either 1 plus I minus 1 or 1 plus recursively n minus f of n minus I. And then I take the minimum over all possible cases. The only thing that you have to be careful is that you could recursively call yourself on the same value many times. So we just have to remember that there are only 4,711 different things you can ask. Just 5,000. And then if I have already seen it, so I set the answers, the table of computed answers to be -1 to indicate that I have not computed it. So at the beginning, I asked if the answer is not -1, then I must have computed it. So I just return it. And then otherwise, I compute it. And then I set the answer table before I return it. And then the only other thing that you have to worry about is the base case when we have recursion. So when you only have when they tell you that it explodes at 1, then that's the end, right? Because the smallest thing that you can put in is 1. So if they tell you explode 1, that's also your answer. So you don't have to do any more tests. So anyway, this is a bit of a recursive thinking and then dynamic programming. This is definitely not the easiest, and it's in terms of dynamic programming, but I want to show you how to think about this problem. All right, so I guess that's the end for this week. And I guess I'll pose another problem sets on Wednesday. Okay, and then I guess it's almost time for school to start, so we'll take a week break at the end, and then come back to the start of the school year, and we'll have some in-person meeting. See you later.